Hi. So we will continue talking about linear transformation. So in this video, we'll talk about two different concepts that's related to linear transformation. One is new linear transformations from old. Second one is the inverses of linear transformation. So here it's like uh, composing two functions. Actually, if here we are given two linear transformations. The first one actually takes a vector from Rm to Rn. And we are given another linear transformation. Let's say it takes from Rn to Rp. So now here, then we may follow T by S to form the composition of the two transformations. And here we just denote this by here S composed with T. Here we have the first transformation and this is the second one. And here in this video, we'll talk about how we combine these two things. Instead of multiplying two matrices, can we just do this by a single matrix transformation? Okay, this theorem says that let T be a linear transformation that takes a vector from m-dimensional space to n-dimensional space. So that is here we have vector V, which is living in n-dimensional space. And by this transformation, we are taking this to n-dimensional space. And we are given another transformation S, which takes this vector, which is living in n-dimensional space, to p-dimensional space. Then it says that S composed with T, that takes from Rm directed from this space to another space. Rp is a linear transformation. Moreover, their standard matrices are related by S composed with T is just equal to the product of these two standard matrices. Okay, so now we'll see one example related to this theorem. Consider the linear transformation. So the first one is taking this two-dimensional vector into a three-dimensional vector. So here we are just talking about a vector which is living in two-dimensional space. So now we have to take this to three-dimensional space under some transformation. Let's say it is, here we have TV. Right. So this one is T. So now we have another linear transformation S that takes a vector from three-dimensional space to four-dimensional space under this transformation. The question is, find S composed with T. So now, can we just find a matrix so that, let's say that compose the thing is, let's say W, if this vector is V, and it just takes directly from here into here. There's four-dimensional space. Can you find a way directly just jumping from here to here? So let's say that matrix is W. Right. So we actually see that the standard matrices of this, the first one, let's say T of xy, which is x, the second component is 2x minus y, and 3x plus 4y. Okay, so I can just write it as the product of this matrix and by xy. So here we have x, so it is 1, 0. This one is 2x minus y, just coefficients, 2 and negative 1, 2 and negative 1. And here we have 3, 4. Here we have 3, 4. So that means that that is our standard matrix for this transformation, right? And for the second one, just write here S U V W. So here we have 2u plus w, 3v minus w, u minus y, v, u plus v plus w. So here we have, can just write it as u, v, and w, right? And just the coefficients, 2, 0, 1. The second line, 3, I mean, we don't have u here, 0, 3, negative 1. And uv, that is, okay. So the first one, all right, UV, and the second one, okay, and the third one, 0, okay. Actually, this one is 4 by 1 matrix, so this one is 3 by 1, so something is missing here. How many variables we have? U, V, W. Okay, U, V, W. So it's 3. So now we need to have one more line here. Okay, 2, 0, 1. Here we have 3, 0, 3, and minus 1. Third one is 1, and this one is minus 1, 0. Okay, I can just rewrite this. Okay, so now I just corrected. I didn't write the third line here. So the third line is U minus V, so it is 1 minus 1, 0, and the last one is 1, 1, 1. So here we have 1, 1, 1. And here we have U, V, W. So that is the standard matrix for this transformation. Let's just denote this by this S. And now, by using the previous theorem 3.2, it says that's, okay, should go forward here. So S composed with T. It says that it's just the product of these standard matrices, S times T. And what is S? S equals S composed T. It's just equal to the product of these standard matrices. So S, you just found this in the previous slide, that is 2, 0, 1, 0, 3, minus 1. And T, it is this matrix. So if you just multiply these two matrices together, we get this matrix. So what is this? It's just our that matrix W. So that is taking that our two-dimensional vector directed to this four-dimensional space. So now if you're given this thing, so here we have, what do we have here? We're just taking this vector U. That is, say that transformation, and it's W, right? It is U. So here we have that is S composed of T, it is U, which is just equal to this matrix, that's W times our vector. And here we have four-dimensional. This one is, this vector is living in four-dimensional space. So S composed of T, X, Y, and here the W is 5, 4, 3 minus 7, minus 1, 1, 6, 3, times, and here we have our vector. So if you just multiply them together, we get 5x plus 4y, the first component, the second component, 3x minus 7, 1, and minus x plus y, 3x plus 3y. Okay, find the standard matrix of the transformation that first rotates a point 30 degrees counterclockwise about the origin and then reflects the result in the y-axis. That is an example for this. So here, the standard matrix of this transformation that first rotates, okay, 30 degrees counterclockwise about the origin. Okay, that's the first one. And then reflects the result in the y-axis. So here, what's going on here? Here, if we are given a point in y in R2, let's say here, we're given a kind of point here. Okay. So first transformation, it should rotate this 30 degrees. Maybe it is somewhere here. Okay. So this one is P of X, Y. And this image is, let's say this P prime. And after that, it says that that reflects the result in the y-axis. And after that, the result, we need to reflect about the y-axis. So here, again, it's just reflect somewhere here. Okay. So maybe if I draw like this, it would be better. You can understand much, visualize things much better. Here, if we have something like this, a vector, first rotate this 30 degrees, comes here. This one is rotation, 30 degrees. And after that, rotating, reflecting this about the y-axis reflection. So let's say P, whose coordinates are x, y, and this one will be P prime, whose coordinates are x prime, y prime, and here we have P double prime, let's say x double prime, and y double prime. So the first transformation, it is T, and we know that C is reflection, I mean the rotation. So let me just use different color here. Okay, so the first one is rotation, about 30 degrees. So here we have the point that is XY, and we are familiar with this matrix, right? It's just 30 degrees. Here we have cosine of 30, sine of 30, minus sine of 30, and here we have cosine of 30. And here we have that vector, x and the y. So which is equal to, here we have cosine of 30, square root of 3 over 2, sine of 30, 1 over 2, minus 1 over 2, square root of 3 over 2. So that is the standard matrix of this transformation. Let's say this one is T. Right. Now the second one, the second thing is reflection about the y-axis. How do you reflect this? If you just reflect the points, these coordinates are, let's say this x, so this will be minus x, right? And the y coordinate does not change because we are just reflecting this vector about the y-axis. At the time here, I can get that, let's say this s, that second transformation is s. So also here we have x and y. So what do we have here? Here we have minus x and the y. So which is to find actually the standard matrix. Actually, just why this is the product of a matrix and the original vector. So here we will have 2 by 2 matrix, and here we have x, y. To get a minus x here, this should be negative 1, this should be 0. And to get y here, this should be 0, this should be 1. So that is the standard matrix of this transformation. Let's say it is S. So now we are going to find a single transformation that actually do these things together in one single, how to say, one single operation. So to do this one, so we need to find this as composed with T, and here the vector, let's say this x and y, right? So to do this one, let me just find this as times T. It says, what is it? Find the standard matrix. That is the standard matrix of this. I can just denote this by, let's say, A. Let's equal to, what is S? S is negative 1, 0, 0, 1. And how about T? T is square root of 3 over 2, 1 over 2, minus 1 over 2, and the square root of 3 over 2. Equals, if we multiply them together, so here we have minus square root of 3 over 2, and multiply by this, it is 1 over 2, and multiply by this, here we have 1 over 2, and by this, square root of 3 over 2. So dot, 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 the standard matrix of these transformations is, what is it? It is square root of 3 over 2, 1 over 2, 1 over 2, square root of 3 over 2. Okay, if you just multiply any vector by this matrix, actually first, it just rotates this 30 degrees anti-clockwise, and after that, it reflects the point about the y-axis. Okay. Now let's talk about inverses of linear transformation. That's the last part of this sub-chapter. Consider the effect of a 90-degree counterclockwise rotation about the origin, followed by a 90-degree clockwise rotation about the origin. That is, we are talking about, let's say, okay, let's just talk about unit vectors. Let's say here we have u, e1, whose coordinates are 1, 0. So now, if we just rotate this 90 degrees, let's say this r, let's denote this by this, here we have 1, 0. If you just rotate this 90 degrees clockwise, it will be here. So that is 0, 1. So it's actually image will be 0, 1. Now, this one actually, what is it? It's just our standard unit vector, E2. Now, how about if I apply this transformation to this, minus 90 degrees of this E2, that is 0, 1. So here now, if I just rotate this 90 degrees clockwise, we will get the origin vector here. So what we have here, and here again, I will get 1, 0. So now using the previous theorem, if I just apply them together, what we have here? So here R 90, and here we have composed with R minus 90 degrees. And if you just apply this to any vector V, right? And here we get back to the origin vector V. Okay. So now in this case, we perform the transformations in the other order, and we just get the same result. It's V. And also, if you just, for example, interchange first, starting from this, first rotate this clockwise direction 90 degrees, and after that anti-clockwise 90 degrees, still we will get the original vector. So that's what we are going to talk about here. So actually that thing, what do we have here? That thing is us I, because I of V, it has no effect on this vector. It just gives us the original vector. So now here, you should actually make sure that when we talk about the inverses or inverse of matrix, actually we mean here that I is n by n identity matrix, right? And also actually here, this rotations, it is taken from R2 to R2. In general, actually when this is the case from Rn to Rn, for other dimensions, if the matrix is not square, we know that inverse is not defined for non-square matrices. Anyway, so this definition says that let S and T be linear transformations from Rn to Rn. Then S and T are inverse transformations if S composed with T equals In. S composed with T, it has no effect on V, and the T composed with S, that's equal to In, that means that their effect is 0 on V. Then actually we call them S and T, they are inverse transformations. Actually, they are inverses of each other. In the theorem, actually, we can just generate this rule. So again, you are talking about this invertible transformation from Rn to Rn. Then it is standard matrix T is an invertible matrix, and its inverse is this. That means it just we need to find if we are talking about this transformation. Let's say it is X, and here let's say it is standard matrix T. Here we have X. If you just denote this by A, here we have AX, right? So then what will be the inverse of this one? The inverse of this will be just A inverse, right? Because A inverse A, if you just apply this A inverse to both sides, and here we will have the original vector back. So immediately let's do two examples related to this, and after this I will finish this chapter. So in example 10, find the standard matrix of the transformation that rotates a point 30 degrees clockwise about the origin in R2. Standard matrix of the transformation that rotates a point 30 degrees clockwise about the origin. So now it is clockwise, right? Okay, in two different ways we can find this. Number one is here. Number one is we know that the rotation of 30 degrees. I mean the standard matrix. Let me just write here. It is X and Y. Right? What is it? If you remember this, it's just this matrix. It is cosine of 30 and sine of 30. We have already calculated this. Let's just do this one more time. Y minus sine of 30. And here we have cosine of 30. Which is, here we have square root of 3 over 2. 1 over 2 minus 1 over 2 and 1 square root of 3 over 2. Okay. In different way also, immediately I can just substitute here negative 30 because negative 30 means anti-clockwise direction. Here I'm just going to make use of the previous theorem. So now that is our standard matrix of rotating 90 degrees. Let's say this vector is vector u. Okay, here we have vector u. Okay. So now how can I just find the standard matrix of the transformation that rotates a point 30 degrees clockwise about the origin? So since actually this one is rotating this anti-clockwise, it is inverse will actually rotate this clockwise. So just if I find the inverse of this matrix, that gives us the standard matrix of the transformation that rotates a point 30 degrees clockwise about the origin in R2. So what is A inverse then? I know how to find the A inverse, number 1 and number 2. To find the A inverse, first we need to calculate its determinant. It's just 2 by 2 matrix. Determinant of A equals square root of 3 times over 2 times square root of 3 over 2. That is 3 over 4 minus 1 over 2 times 1 over 2. That is minus 1 over 4, which is equal to 1. Good. And after that A inverse will be, here we should just interchange this A and D, and after that multiply these numbers by negative 1. So since they are actually same, so here we have square root of 3 over 2, square root of 3 over 2, multiply these numbers by negative, so here we have minus 1 over 2, 1 over 2. So now if you multiply any vector by this matrix, it actually, its effect will be the rotation of that vector clockwise 30 degrees about the origin. Okay, the last example, determine whether projection onto the x-axis is an invertible transformation, and if it is, find its inverse. And if you remember this, in the previous examples, we did this example, not in this example, that's matrix. So the projection of the point on the x-axis, if this one is x and y, is projection onto the x-axis. This one is x-axis, this one is y-axis. This projection on the x-axis will be x and 0. And if you remember, it is matrix was standard matrix. The standard matrix was, what is it here, this, let's say this transformation xy to x0, it was 1 0 0 0, and here we have xy. Now since it is standard matrix is this 1 0 0 0, and its determinant is equal to 0 0 is equal to 0, that means that it is not invertible. So that means that actually, what is it? So since it's not invertible, we cannot find its inverse, so that's not invertible. We don't have any matrix, it's just actually puts this point back here. Why? Because the projection of this point onto the x-axis, it is unique, it is here, right? Now, if you talk about this projection of this point on the x-axis to where? Here to this line or to this line, where? It's not mentioned here. It is infinitely many points here above this point. And that's actually also, that's why it doesn't have inverse. Okay. Thank you very much. That's the end of this chapter. So in our next videos, we will talk about chapter 4. Bye-bye.